In this video tutorial, we will introduce the concepts of molecular polarity and intermolecular forces. Now, if you recall, electronegativity, En, is the relative measure of an atom's ability to attract shared electrons in a chemical bond. The higher the En value for the atom, the greater its attraction for electrons. And of course, the lower the En value, the less of an attraction it has for electrons. Electronegativity difference, on the other hand, delta En, provides us with a guideline to identify the polarity of a bond, so how much charge separation is there between the two atoms. So oxygen, for instance, has an En value of 3.5, while hydrogen has an En value of 2.1. As such, oxygen, with its higher En value, will pull the electrons in the chemical bond closer towards its nucleus because it has a greater attraction, and thus this end of the molecule is going to have a slightly negative charge, leaving this end, since it has less electrons hanging around it most of the time, slightly positive. Now, if the difference in their electronegativities is of large enough value, say anywhere from 0.5 to 1.7, then we say the charge separation is only slightly negative and slightly positive, which is represented by the lowercase d in Greek letters over here. But if there's a large charge separation, then it's going to be an ionic characteristic, and so you'll have definitely a negative charge because the electrons have been ripped and transferred over to the other atom, and a definitely positive charge because it has permanently lost or transferred its electron to the other atom. On the other hand, if the En difference is very, very low, say somewhere between 0 and 0.5, we say that bond has nonpolar covalent characteristics. And that would occur where the atoms are sharing the electrons equally. And since they're sharing the electrons equally, neither side gets electron more than the other, so neither side is going to be more negative or more positive than the other, at least not significantly anyway, resulting in a net charge of close to 0, or very little polarity. So polarity means to have opposite ends, and if both sides are going to be this almost the same charge, then you're not going to have much of an opposite. Versus if it was a polar covalent bond, slightly negative, slightly positive, because the electrons are spending most of their time around here, but every now and then going back over here, then we say there's some slight polarity, some slight polar nature to this. All right, slightly negative, slightly positive, slightly opposites. Versus, of course, if you have an ionic compound where the electron is permanently transferred to one side and leaving the other side with a deficit, then that's definitely very polar, to the point where it's ionic. But again, please keep in mind that these values, 0.5 and 1.7, they're arbitrary. If you look at a different textbook, you'll see different numbers. They are just there to give us a guideline of when we'll start to see polar covalent properties, when will we start to see ionic properties. Just like this color spectrum over here, I know where yellow is. Well, I know where nonpolar covalent is, I know where ionic is. But where exactly does the yellow start? Some might say here, some might say here, well, same thing. I can't say that at 0.5 that's exactly when polar covalent part starts, but I can say that at 0.5 you'll start to see some polar covalent properties. Same with the 1.7. That's not where ionic has to start. That's where you start to see some ionic characteristics. So quite often I will say 0.5, even 0.4, anywhere plus or minus 0.1 of these boundaries. So for instance, if I had 0.4, I could say it's weakly polar covalent. Or 0.5 or 0.6, I could say weakly polar covalent. Versus over here, 1.6, 1.7, 1.8, you could either say it's strongly polar covalent or weakly ionic. All right, so I rarely ask my students, is this going to be an ionic bond? Is this going to be a polar covalent bond? No. Typically what I'll ask is I'll compare these two bonds. Here's one bond, here's the other bond. Which one is more polar? So for instance, if you look at this, it's carbon versus hydrogen, where carbon's En value is 2.5 and hydrogen's is 2.1, if I look at their delta En value, it's 0.4. 0.4 is technically nonpolar covalent, but I can also say it's weakly polar covalent. So a common test question I would ask is, between a CH bond versus an OH bond, which of these two bonds is going to be more polar or have more polar characteristic? Well, if you look at the OH, has a delta En of 1.4, so it's a much bigger charge separation, with the electrons spending most of their time around the oxygen and very rarely coming back to the hydrogen, you're going to see a partial negative, partial positive. Versus CH, because they're very, very similar in the electronegativity, so not much of a difference, you're going to see the electrons spend more time around the carbon rather than the hydrogen, but not as great of a difference as you would of the OH bond. And because of that, you're not going to see the big, giant charge separation of a big, slightly negative, big, slightly positive. It'll be a smaller, slightly negative, and a smaller, slightly positive. All right, so the polarity of the OH bond is greater than the polarity of the CH bond. So to represent this, we draw something called a dipole moment. Now, a dipole moment is a vector quantity, meaning it has both magnitude, so that's size, and direction. Dipole moments are there to show the migration or the movement of electrons due to the electronegativity differences in the atoms. All right? So if I've got electrons in the chemical bond, which direction are they moving towards? Which atom is more electronegative or attractive for electrons? So of course the arrow shows the direction in which the electrons are moving. So in this case over here, the oxygen is dragging the electrons towards it, and that's why the arrow is pointing this direction. If you recall, electrons are negative, so where they're moving towards, that end will be slightly negative. And where they are leaving, that end will be slightly positive. Hence, this little symbol at the end kind of looks like a positive sign. Now, in both these cases, the left atom is the one that's more electronegative. So that's why the arrow is pointing towards the carbon and pointing towards the oxygen. And so electrons spend less time around the hydrogen in both cases, resulting in a slightly positive charge on this end. Since the En difference in OH is significantly larger than that of CH, that means electrons spend a lot more time around the O than they would around the C. As such, the dipole moment in a CH bond is much smaller than the dipole moment in a OH bond. Now, in future courses, you will have to draw these magnitudes to scale. So maybe you would say 1 centimeter represents a 0.1. But for this course, all we're going to do is we're going to qualitatively identify which direction it's going and qualitatively say, oh, this one's bigger than the other one. So we don't have to draw it to scale necessarily. So that will simplify our questions significantly. Now, a common mistake students make is being unable to differentiate between a polar bond versus a polar molecule. They are not the same thing. Polar molecules are made up of polar bonds. It's like saying a sports engine and a sports car are the same thing. No, a sports car requires a sports engine, but there's more to it than just having a really powerful engine. There has to be aerodynamics, etc., etc. So similarly, the presence of polar bonds within a molecule doesn't necessarily mean the molecule itself is polar. I can't just take a sports car engine, put it into a smart car, and automatically the smart car is a sports car. No, because you have to worry about aerodynamics. Once you pass 130 kilometers per hour, a smart car will flip over. Its aerodynamics does not allow it to go very fast, even if you had a very powerful engine within it. Well, similarly, the molecule's geometry must also be taken into consideration. Let's take a look at carbon dioxide, for instance. So, oxygen has an En value of 3.5, while carbon has an En value of 2.5, so their delta En is 1.0. An En difference in the 1.0 range is well within polar covalent, so we're going to have partial charges involved with this particular bond. As such, we're going to draw in our dipole moments. Here's the oxygen, which is more electronegative, so for this specific bond, the electrons are being dragged towards the oxygen end, so that's why we draw the dipole moment in this direction. This is another oxygen. We can do the same thing. So electrons in this particular bond are being dragged towards the oxygen because that's the higher En value. It's more attractive for electrons. You'll notice that both dipole moments are equal in magnitude because they both have a delta En of 1.0. All right, they're just pointed in opposite directions. So here we have a polar covalent bond. However, according to Vesper, Cl2 has a linear geometry. And so although it's got a polar covalent bond, the overall molecular geometry does not allow for polarity. That's like saying I've got a sports car engine in a smart car, but the aerodynamics does not allow it to be considered to be a sports car because it can't go too fast, otherwise it would flip over. Well, same thing over here. Even though there's charge separation, because of the geometry, there is no opposite polarity. I mean, the word polar means opposite ends, but if you look at it, partial negative, they're identical. There is no opposite ends to this. There's no north pole, south pole, positive, negative. It's partial, negative, partial, negative. So, to test whether a molecule's geometry allows for polarity, we're going to add the vectors, the dipole moments, head to tail. So the head of one dipole moment is added to the tail of the other dipole moment and see where they're going. If the electrons overall move to one end of the molecule, then you've got polarity because now one end will be negative and the other end will be positive. But in this case over here, they're being pulled left, but then they're being pulled right. And so you started here and you ended here. The electrons haven't gone to one end more than another, so you have no polarity. All right? So since each bond is identical, their magnitudes are identical and differ only in direction. Once added, we see there's no displacement or change in position. The vectors have canceled each other out. As such, without a net dipole moment, Cl2 is considered to be non-polar. All right? It has polar bonds, but it is a non-polar molecule overall. But if you take a look at water, for instance, so H2O, the delta En for OH is 3.5, for oxygen, 2.1 for H. When you subtract them, you get the delta En, the difference between the two, which is 1.4. 1.4 is well within the range of polar covalency, so we're going to have some partial charges. As such, I'm going to draw my dipole moments from the hydrogen towards the oxygen because the oxygen is more electronegative. So there's my dipole moment moving towards the oxygen for that bond, and for this bond, draw a dipole moment as well. So you're going to have to draw a dipole moment for every single bond in the actual molecule itself. Now, according to Vesper, water has a bent geometry. All right. So what we're going to do is we're going to add the vector quantities head to tail, and we'll see that overall we started here, but we ended up here. So it looks like the electrons are migrating towards the top, towards the oxygen end of the water molecule, leaving this end partially negative and this end partially positive. So now we have a north pole and a south pole, a negative pole, positive pole, or at least partial negative, partial positive. And so this molecule does allow for polarity. Its geometry allows for polarity. As such, water is considered to be a polar molecule with a negative dipole, one end, and a positive dipole, the hydrogen end. Now, if you recall, we call it a dipole because di means two, pole meaning ends, and there are two ends, the partial negative end, the partial positive end. Now, when it comes to adding up the vectors, it doesn't matter if you added this dipole first, then this one, or if you added this one and then this one. Just as 3 plus 2 plus 1 is the same as 2 plus 3 plus 1, it doesn't matter what order, adding this dipole first and then this one still gives you the same result. I'm starting here, I'm going up towards the oxygen. All right. Now, sadly, more complex molecules will require you to imagine how these dipole moments are going to be added up in 3 dimensions. Now, thankfully, for this course, we're only going to look at it qualitatively, so all I need you to know is which end of this molecule is going to be more negative and which end is going to be more positive. So if you look at this one over here, imagine yourself as a diver, that you are the central atom, and you are attached to 4 dolphins, for instance. So one dolphin is pulling you up, the other dolphin is pulling you down. Well, which way are you going? Are you going to go up or are you going to go down? If those dolphins are of equal strength, you're not going anywhere because their forces will cancel each other out. But I do have a dolphin pulling me into the page, going forward, and another dolphin pulling me out of the page, going forward. Now, because the dolphins are of equal strength, pulling me into the page and pulling me out of the page, those kind of forces will cancel each other out, but both dolphins will be pulling me forward, making this end of the molecule partially negatively charged and leaving this end of the molecule partially positively charged. And so my dipole moment overall, the net dipole for this particular molecule, is to move forward. Same scenario here. You are the diver connected to 3 dolphins. One dolphin is trying to pull you in this direction. The other one's pulling in this direction, pulling in this direction. If we looked at it from the top view, it would look like you were being pulled in these 3 directions. But because they're equally being pulled, you're not going to move in any direction overall. But because they're all pointing down, you will be moving down this way so that the electrons gather around this end of the molecule, giving it a partial negative charge, and then they make this one a deficit of electrons, so then it's going to be partially positive. So the overall net dipole for this specific molecule is to move down. All right, so these are 2 polar molecules as they have polar covalent bonds that are arranged in a way and a geometry that allows for polarity. Now remember, it's not just direction that you have to factor in, you also have to factor in the magnitude. How big of a charge separation is there? So in this case over here, a tetrahedral shape like CH4, if we look at it and every single one of them is identical in terms of its charge separation, because they kind of point off in a way that cancels each other out, there's going to be no net dipole moment for CH4. But in this molecule over here, it's like being pulled by 3 dolphins in this direction, but 1 whale. Because the whale is generally stronger than the dolphins, you're going to be pulling electrons more towards this end than you would with these. So it's an unequal attraction of electrons, where the electrons are being dragged mostly towards this end of the molecule, leaving it with a partial negative at the top over here, and a deficit of electrons down here. So the overall net dipole for this molecule is to point up. Similarly over here, I've got 2 dolphins pulling this direction, and then 2 whales pulling this direction, so that makes this end of the molecule more negative, leaving this end of the molecule more positive. And same thing for this one. We've got the electrons congregating around this end and a deficit on this end. So we have polarity in both these cases. In both these cases. On the other hand, if we look at this example over here, because it's like being pulled by 4 separate whales, each with the same amount of strength, that again will cancel each other out, so there's no net dipole moment for this. Alright, so what is the purpose of knowing whether a molecule is polar or nonpolar. How does that help? Well, if something is nonpolar, so there are no opposite ends, then the attraction between molecules is going to be pretty weak. So we say it has a weak intermolecular force. All right? Now, the intermolecular force is the attraction between two separate molecules. And if this intermolecular force is weak, then of course we're going to have a low melting point, low boiling point, and low solubility in water. Meanwhile, if the molecule is polar with a partial negative, partial positive, so opposite poles, then the dipole of one molecule will attract the dipole of the other. And the greater the charge separation, the bigger the delta En, the greater their intermolecular attraction. Now, please remember, intramolecular force refers to what holds the molecule itself together. That has nothing to do with melting points, boiling points, or solubility, because that would be a chemical bond. All right? We don't break chemical bonds during a physical change. We only break the intermolecular force. Now, in general, there are three types of intermolecular forces we're going to be dealing with. The first is a dipole-dipole attraction. Right? So the partial positive dipole of one molecule attracts the partial negative pole of another. So that would be what we talked about, dipole-dipole attraction. Now, dipole-dipole interactions can only exist between polar substances. If the substance is nonpolar, there will be no dipole-dipole attraction. And this accounts for the moderate melting point, boiling points of polar substances. All right, so their melting point, boiling points will not be as low as if they were neutral-neutral, but they won't be as high if it was a definitely negative and positive, like an ionic compound. Then it'd be really attracted to each other with a very high melting point, boiling point. Now, the next type of force is called dispersion forces, or London forces. Sometimes you may hear them being called van der Waals forces. Let's watch this quick little video clip.
The movement of electrons around a molecule is to some extent random. This means that, at a given instant, the electron cloud may be concentrated momentarily at one end of the molecule. This creates a temporary dipole, called an instantaneous or temporary dipole, because it exists only for a very short period of time. In a collection of molecules, a momentary concentration of electrons at one end of a molecule repels the electrons in another, adjacent molecule. In this way, one instantaneous dipole induces another dipole in a neighboring molecule. The dipoles attract each other by electrostatic forces, termed dispersion forces or London forces. Dispersion forces oscillate rapidly, being continuously turned on and off as the electrons continue their movement around the atomic centers. Because they appear only momentarily, they are rather weak on average. All the same, they are present in all molecules, regardless of their polarity. Dispersion forces are the major attracting forces in substances composed of molecules, especially nonpolar ones.
So, as we saw in that video clip, dispersion forces are the result of the random motion of electrons. Every now and then, electrons may, for a split second, accumulate on one side of an atom because their motion is random. That, of course, would make that side of the atom slightly negative, while leaving the other side with a deficit of charges, so it'd be slightly positive. Since this is only temporary, only lasting for fractions of a second, we call this a temporary dipole. But you'll hear them being called dispersion forces, London forces, or van der Waals forces. Now, please note that these dispersion forces only last for fractions of a second, so they're very weak, very short-lived, and they are influenced by the number of electrons and the number of atoms within that molecule. So the more electrons there are, the more they can randomly shift to one end, giving it a higher partial charge. But in the end, they are the weakest of all the intermolecular forces we'll be looking at, and they are present in every single molecule. So what I mean is, in an ionic bond, you'll have strong ionic attractions, but you'll also have weak dispersion forces present because those electrons can still randomly move to one end, adding to the strength. In a polar covalent bond, or a polar molecule, you'll have moderately strong dipole attractions, so dipole-dipole attraction, and you'll also include weak dispersion forces, so the dispersion forces are still present in here as well. And finally, with a nonpolar molecule, you just rely on weak dispersion forces to hold the molecules together. Now, the reason why we don't really worry too much about weak dispersion forces when it comes to ionic compounds or polar molecules is because in comparison to the dipole-dipole attraction or the ionic attraction, it's negligible. So for instance, let's say I was towing a boat behind my car. If I use a metal chain, that would be like using an ionic bond to hold them together. The ionic attraction is very, very strong. But what if my child said, oh, let me help, and decided to put a piece of tape across from here to here? That would be negligible. Sure, it might help, sort of, but it's negligible. I'm not going to factor that in to my carrying capacity. All right. When it comes to polar molecules or ionic compounds and their intermolecular forces, the attraction that holds them together, weak dispersion forces are negligible. We don't really have to worry about it. Now, if I don't have a metal chain and all I do have is tape, then yes, I do have to worry about the tape that's holding them together. It's probably not going to work in any case. But if that's all I have, then weak dispersion forces do become something that you have to factor in. Alright, so the final intermolecular force we're going to be looking at is called hydrogen bonding. Let's watch this quick little video clip.
In liquid water, positively charged hydrogen atoms of one water molecule are strongly attracted by the lone electron pairs of negatively charged oxygen atoms from other water molecules. This type of intermolecular interaction is called hydrogen bonding. Every water molecule can form 2 hydrogen bonds through hydrogen atoms, and 2 through electron pairs on the oxygen atom. As a result, intermolecular interactions in liquid water are exceptionally strong, which is reflected by the high boiling point of water, 100 degrees Celsius. In solid ice, water molecules are held together by a regular array of hydrogen bonds. Relatively large empty spaces in the crystal lattice account for the low density of ice and also explain why ice floats on liquid water.
So, as we saw in that video clip, when hydrogen is attached to a highly electronegative atom, such as oxygen, nitrogen, or fluorine, as you can see, those elements are very electronegative with high EN values of 3.0, 3.5, and 4.0, you end up with a highly polar covalent bond being formed. This results in very large dipole moments, and so you'll have a partial negative end of the molecule, a partial positive end of the molecule, and they will be attracted to each other. We call this a hydrogen bond, even though technically it's not a chemical bond, so it's not a exchange of electrons. It is still an intermolecular force, but for some reason they just call it a hydrogen bond because it's one of the strongest types of intermolecular forces. Quite often, these hydrogen bonds will also involve lone pair electrons. So with water, for instance, oxygen has 2 lone pairs at the top, adding to the more negative polar nature of the molecule. So this end is more negative, this end is more positive. And so the partial positive attracts to this partial negative as well as the lone pair electrons floating around here. So that just adds to the electrostatic attraction between water molecules and the power of this hydrogen bond, this attraction for the hydrogen bond. So hydrogen bonds are still considered to be dipole-dipole forces, but due to the large charge separation, due to the highly polar nature of the bond, we get abnormally high melting point boiling points than what we would normally see in a regular dipole-dipole attraction. So here's a chart that outlines the electrostatic attraction between atoms, going from the weakest London dispersion forces, which are temporary dipoles, all the way to the strongest, which are ionic bonds, where it's definitely a positive, definitely negative charge attracting each other. Please keep in mind that these rankings are generic, so they're not always going to be true. Take a look at ionic bonds. They have a range between 400 kilojoules per mole all the way to 4,000, while covalent has a 150 to 1,100 range. So technically you could have an 1,100 kilojoule per mole covalent bond versus a 400 kilojoule per mole ionic bond. And so in that case, that covalent bond will be stronger than the ionic bond. It's just that in general, ionic bonds tend to have a higher upper range, while covalent bonds have a lower upper range. Alright, let's do a sample question. So for examples 1 through 5, try to identify the main type of intermolecular force or the strongest type of intermolecular force present in each of these compounds. Alright, so the first thing we're going to do is we're going to draw out the 3D Lewis structure and see what kind of Vesper shape it's going to have. Once we have identified carbon disulfide as having a linear shape, we're going to calculate the delta En for each and every chemical bond present. Carbon has an En value of 2.5 and so does sulfur. And when we calculate delta N, we find that 2.5 minus 2.5 is 0, so overall this molecule is going to be nonpolar. Without polarity, the molecule is not really attracted to another molecule, and so we just have to rely on temporary dipoles forming, so through the random motion of electrons. So the primary intermolecular force is going to be London dispersion forces, which is one of the weakest ones. Moving on to number 2, we're going to work with ammonia. From here we see that it has a trigonal pyramid shape, and here's the 3D structure. So now we can take a look at its En values. Nitrogen has a 3.0, while hydrogen is only 2.1. And the dipole moments will be moving towards the nitrogen. Due to the geometry, we now have polarity, where one end of the molecule is going to be partially negative because electrons are ultra attracted towards the nitrogen, and leaving the bottom end where the hydrogens are with electron deficit, and so that end is going to be partially positive. And when the partial negative end of one ammonia molecule is attracted to the partial positive end of the other ammonia molecule, we form a dipole-dipole attraction. As was mentioned earlier, due to the electronegativity of nitrogen and also that lone pair electron at the top, we can form a very, very strong dipole-dipole attraction called a hydrogen bond. Alright, now just be careful, just because there's a hydrogen in the molecule doesn't mean a hydrogen bond will form. It has to occur typically between hydrogen and one of these three elements over here, nitrogen, oxygen, fluorine. Those are where you're most likely to encounter a hydrogen bond. So just because there's a hydrogen in there doesn't mean there's going to be a hydrogen bond. You have to see it being attached to an electronegative atom like oxygen, nitrogen, or fluorine. Alright, moving ahead, let's look at oxygen. So we're dealing with 12 electrons in total. Now with oxygen, there's no choice. It has to be linear. I mean, there's really only 2 points. There's no other shape you could have. And looking at the En value, we see it's 3.5. With both En values being identical, so the delta En is 0, that means it's going to be nonpolar. So the electrons will not be attracted to one end more than the other, so you're just going to have a nonpolar molecule. Again, with two neutron molecules, the only attraction they're going to have is due to those instantaneous dipoles, the temporary dipoles that form through the electrons moving randomly. And so we're just going to call it London dispersion forces will be the strongest type of IMF between these two. Our fourth example is CH2F2. This results in a tetrahedral shape. The En value for hydrogen is a 2.1, while carbon is a 2.5, and fluorine is a very high 4.0. So for the CH bonds here and here, the electrons will be moving towards the carbon, as we see with the dipole moments. Meanwhile, the electrons in the CF bonds are moving towards the fluorine because it's more electronegative. So the overall net dipole is to have the electrons move towards the fluorine end of the molecule, making this end partially negative and leaving this end partially positive. And so this molecule is polar. Due to the polar nature, we now have a dipole-dipole attraction between the two. Just be aware, however, that there is no hydrogen bonding here. So even though there's a hydrogen, and it is slightly positive, it's not super positive. Because with the hydrogen versus the carbon, the electrons are not being dragged so much in this direction to make this a very positive. Alright? If you recall, only when hydrogen is bonded to a very electronegative atom, like nitrogen over here, can you have a very polar covalent bond. Even though the fluorine is present and it is very electronegative, it is not interacting directly with the hydrogen. You notice the hydrogen is bonded with the carbon, it is not bonded with the fluorine. As such, the bond formed between the H and the C is not very polar. So the electrons in this bond will not be dragged towards the carbon, creating enough of a charge separation that would allow for hydrogen bonding. So just a regular dipole-dipole attraction exists between these two molecules. Alright, and then now our last example is C2H6. So here we're going to have a tetrahedral shape around each of the carbons. So the carbon over here has a tetrahedral shape, and so does this carbon when it's attached to it, another tetrahedral shape. Hydrogen has an En value of 2.1, while carbon is 2.5. Resulting in very, very weak dipole moments, but more importantly, these dipole moments kind of just cancel each other out. Therefore, the molecule is nonpolar, and we're going to have to rely on London dispersion forces to attract two separate molecules of ethane. And so the electrons would have to all randomly move to one end in order for this attraction to occur. So very, very weak London dispersion forces due to the instantaneous dipoles that are required to form. Now, by identifying the type of intermolecular force that is most prevalent in each of these substances, we can start to order them from lowest to highest melting point using this chart over here. As you can see, hydrogen bonds provide pretty strong attraction between molecules, so there's going to be a lot of energy required to separate the two molecules, and that results in a higher melting point, negative 78 degrees Celsius, in comparison to all the other ones. That is followed by regular dipole-dipole attractions, and then finally London dispersion forces should be the weakest ones and the easiest to remove, so very little energy. Low melting points are required to separate them. Now, in situations where you have to compare between multiple London dispersion forces, which one is going to have the higher melting point? Whichever one has the most number of electrons is going to have the higher melting point, and whoever has the least number of electrons would have the lowest melting point. That's because if you had all 38 electrons randomly move to one end of the molecule, that's going to make that end more negative than if you just had 16 electrons moving to one end as opposed to 38. Now, if you had to compare between dipole-dipole attractions, just look at their delta En values to see which one has greater charge separation and thus the higher melting point. Now, there is a discrepancy here. You'll notice that carbon disulfide is a London dispersion force, while CH2F2 is a dipole-dipole attraction, and yet carbon disulfide has a higher melting point than CH2F2. So as I mentioned before, what we've learned here is just part of the picture. It's not the full, complete explanation. There are other factors that we have not covered, as they are beyond the scope of this course. So carbon disulfide is one such exception. I believe its anomalous behavior is due to its molecular symmetry. But again, that's beyond the scope of this course. So on a test, what would happen is I would only give you examples that do fit what we've just learned, that do follow the patterns, that will not be anomalous, that will not be weird exceptions that you are unable to predict. All right? So what I would like you to do now is to continue on the rest of this worksheet. Answers are located at the back over here on the last, I think, 3-4 pages. If you have any other questions, just let me know. Now, the final topic we need to discuss in this unit is that of aggregates. The properties of pure substances are not based solely upon the individual particle, so we can't just look at the atom or the ion or the molecule by themselves in order to determine their physical or chemical properties. Instead, aggregates, or groups of particles, and the way they are held together by attractive forces have a significant impact upon their physical and chemical properties. Now, in this course and in grade 11, we discussed already the ionic crystal, the molecular crystal, and the metallic crystal in a previous lesson. So I'm not going to spend too much time on these. Essentially, ionic crystals held very tightly together, and that will affect their melting points, their boiling points, how well they dissolve in water, and to what degree will they conduct electricity. Same thing for molecular crystals, and finally metallic crystals. The new term I want to discuss over here is that of network solids. These are compounds in which the atoms are bonded covalently in a continuous network. With molecular crystals, it's pretty easy to identify which two atoms are covalently bonded. All right, so this is one molecule that's covalently bonded, so are these ones, and this is a separate one. So these are three separate covalently bonded molecules, all held together by intermolecular forces. But with network solids, there doesn't appear to be a beginning or an end. I cannot identify individual molecules. Instead, I can think of the entire crystal as one big giant macromolecule. So, if I ask you to draw silicon dioxide and draw me the Lewis diagram, most of you would probably draw it in this manner. But when we do experiments, we found that actually there is no double bond between the silicon and the oxygen. We instead see 4 single bonds with 4 separate oxygens bonded to each silicon instead. Since there is no natural beginning or ending that exists in this particular pattern, it is considered to be a network solid, with silicon dioxide being the simplest repeating pattern or the simplest repeating unit we can see in this molecular structure. Now, again, don't freak out. I don't expect you to know when a network solid is going to appear, which situations will they occur, but I do need you to know what is a network solid and provide me with an example. All right, now the last aggregate we're going to look at is called allotropes. These are compounds that are comprised of the same element, but differ in the way these elements combine together. All right, this of course results in them having different physical and chemical properties. The most common example of an allotrope that we like to use is that of carbon. All right, now carbon has 3 major allotropes: graphite, diamond, and fullerenes. Take a look at these 4 examples over here. They're only made up of carbon atoms, but the way these carbon atoms are assembled gives them totally different properties. Take a look at graphite. We use it in pencils to make marks on paper because as we drag the graphite across a piece of paper, sheets of the carbon slide off, which we use for writing. But you wouldn't want to use a diamond to write on paper because diamonds are very, very hard. They just rip off the paper itself. They won't slide off. And that is due to this shape for diamonds. This rigid shape provides extreme strength, and that's why diamonds are extremely hard and tough substances. Then finally with fullerenes, well, their molecular structures provide them with extremely interesting properties, like the ability to conduct electricity better than copper, stronger than steel, and extremely lightweight. So while a single atom, ion, or molecule may have certain properties by themselves, when you put them in groups and assemble them together, how they are able to attract each other, how they are grouped together, totally affects their physical and chemical properties.